Hey there, class. We are starting podcast 2.2. We're going to actually get into the meat of forces and what they entail. So we're going to talk about Newton's first and second laws, and then we'll talk about the third law in a later podcast. All right, so before we can talk about Newton's first and second laws, which deal with motion, we have to talk about forces. Okay, so there are different types of forces, and we'll get into those later, but right now we need to be concerned with a net force. Okay, a net force is an overall force, and it's where you equal up all the forces that are acting on an object. Well, if all the forces are balanced, meaning that well, let's go to unbalanced because that's listed first. All right, so if we add up all of the forces that are being applied to an object, if there are forces that are acting in opposite directions, they would actually subtract from each other. And if there are forces from the same direction, they would add together to give your net force. And if that net force here, looking down here, if that net force is gives a number greater than 0, it's going to cause the object it'll cause the object to move if it's staying still, or to stand still if it's moving. So it'll slow it down, or it'll actually move it. So unbalanced forces, when there's an unequal force that acts on the object. So if you and your friend were pushing on this big block and your friend's bigger than you or has more strength than you, there's a chance that big block could end up falling on you. All right, so for balanced forces, that's when your net force equals to 0. So all forces acting on it cancel each other out. And that will typically, it means that the object stands still because it's not moving. But if it's something that's in motion, it'll keep moving until something unbalances it. Okay, so if you and your friend are pushing on this block right here and you both use the same force, the block's not going to go anywhere. Okay, here's another example. Weak force is pushed on to the right, a strong force is pushed on from the left, and so the net force moves the block in the direction of the strongest force. All right, why does that have to do with anything that we're doing? Well, because in motion, you have forces acting on you to get the things moving and or stand still. All right, so Newton's first law of motion says that an object at rest and an object in motion will maintain their, so an object at rest will stay at rest, or an object in motion will stay in motion unless it experiences a net force. Okay, so this is also known as the law of inertia. We'll talk about inertia in just a second. So objects are going to tend to maintain their state of motion. If you are someone who goes home and sits down on the couch, typically you're going to stay on that couch until something forces you to move, right? I know, I'm guilty of it. All right, however, if you are someone, and you probably know someone, who constantly moves, okay, my daughter moves all the time. She runs from area to area. She won't stop, okay? She's going to continue to run because she has that energy to run until I force her to stop and sit still, okay? A force must be applied to change the velocity. Now, just because something's not moving doesn't mean it doesn't have a velocity. It'll be 0 velocity. Okay, it's not moving, so it would be 0. To get it to move, you have to apply that force. All right, so the first law of motion is what happens when no net force is acting on an object. So the forces are all balanced. All right, so inertia. We said we would talk about that. Well, inertia is the tendency of an object at rest to remain at rest, or the tendency of an object that's moving to remain moving at constant velocity and in a straight path. That's important, in a straight path. And I'm writing with my mouse, so it's not big or pretty. Sorry. All right, so it's going to stay at rest, or it's going to keep moving at a constant velocity and in a straight path. In order for it to turn, it would have to have a force acting on it. All right, so here's an example of something remaining at rest unless a force acts on it. Okay, everybody loves Garfield, and if you don't, I'm sorry, but we all love Garfield. So Garfield's lazy. He says, no, I'm conducting a science experiment, thank you. He says he's testing the first law of physics. Bodies at rest tend to stay at rest, but John's calling him lazy. All right, well, what about something that's in motion? If something's in motion, it's going to continue to be in motion at a constant velocity and a straight path unless a force makes it stop or move. So here's an example of motion. Okay, the bicyclist was riding and he hit a wall of tires, and so his body, because it was with the bike stops, but guess what, his body, it needs to keep going, so it's going to keep going until it is acted on upon by an external force. So the external force in this case, when he keeps going, will either be that fence if he's close enough, but I don't think he is, or the ground. Okay, so inertia is where that body wants to keep going. Okay, think about it. When you're in the car and somebody has to slam on the brakes real quick, your body wants to keep going forward. Why? Because it was already going forward and it needs to be stopped by something. Hopefully you have your seatbelt on, and the seatbelt is the force that stops it. If you don't, well, then if you're in the back seat, the seat in front of you, or if you're in the front seat, the dashboard or the window shield, or the window. And if the window isn't enough of a force to stop you, you go through the window, and that's never a good thing. All right, for inertia, if you have a small mass, there is a small force needed to get you to move, you have less inertia. Okay, if there is, well, look at this van. Okay, so this van here is a smaller body substance. There's a small force being applied to it, so the woman is pushing it. It has less inertia. However, if there's something that has a large mass, you need larger force to move it. It has more inertia. For example, this huge dump truck. Do you think that this lady here would be able to push this large dump truck by herself? Probably not. Look how many big guys are needed. There's one here, 2, 3. There looks like another pair of legs back here. So at least 4 guys are pushing on this one dump truck because it has a large mass. It needs more force because it has more inertia. It wants to stay still. Once it starts moving, they're in trouble though, right? Okay, here's another example of Newton's first law of motion. Remember, something is going to be still. It's going to be still until an outside force is acted upon it. So look at this guy's face. Okay, look at this guy's face here. Typically, this guy's face is going to be nice and out and structured, but here comes the boxing glove. There's your external force that's acting on it. It's not looking so hot, right? Oh, okay. Move on. Newton's second law of motion. This one is dealing with unbalanced forces. Okay, the first one was when there was a balanced net force. Okay, so or a balanced force or no net force. On this one, it's an unbalanced force, so there is a net force pushing in one direction or the other. Okay, so the unbalanced force acting on an object equals the object's mass times its acceleration. So the formula for that would be force is equal to mass times acceleration. F is force, m is mass, and a is acceleration. Okay, so here's an example of Newton's second law. You might be familiar with this, you might not. Okay, so you've got a car driving east, and on the same road, here's a deer running west. What's going to happen when the two meet? Well, they both have force, right? But one of these is going to have a little more force than the other. Which one do you think it is? Well, he's got a lot of antlers there, so that would be like, I don't know how to count that. It would be a lot of number bucks. So it's going to be a pretty massive thing, but unfortunately this car is more massive. So what will happen is when these two collide, this deer, this poor little deer, is going to go flying, but because it had a lot of mass to it and a lot of inertia, it's going to damage up the front of this car. It might be totaled, right? But this deer is going to go flying, so the net force on this will continue to go forward because there was less force here. All right, mass and acceleration and force, are they related? All right, so if we take the same force and apply it to two objects, here we have two people. They're getting ready to race the same wheelie chairs. They're racing, same amount of force is applied. What happens? Well, the large mass with the same amount of force, he has a low acceleration, so he's not going to go as fast. Okay, what about the small mass? Well, look, the small mass girl, she's happy because she won the race, because she applied the same amount of force, but it went further because it was a smaller mass substance. All right, well, let's think about it in another way. What if we had a difference in force, but we had the same mass? Well, if we had this little girl here and we pushed her with a small amount of force, she would just go a little ways. The same girl, if we pushed her with a large amount of force, she would go a lot further. So they are related. All right, and then to leave you off with this, here is another example of the first law of physics. Things in motion tend to stay in motion, while things at rest tend to stay at rest, and that's why it's easy to stay awake through the night, but hard to wake up first thing in the morning. All right, I'll see you in class.